All right, welcome back. So I'd like to talk about the time complexity for binary search, how it performs, let's just say, on an array. So as the length of the array grows, a sorted array, of course, how does the time complexity grow in relation? And you can see here on the left, worst and average case are O of log n. And I'll come back to that and why that is. Best case, of course, is O of 1 because it's possible that the very first thing we pick is the element we're looking for. If we pick the middle point of an array, and that's what we want, well, that's one operation, it's constant time O of 1. That's pretty rare, but it's possible. Worst and average case are both O of log n, and I have a couple slides to detail how we get log n. If you're not familiar with logarithms and how this applies to big O, I have a quick video. I think it's the last video of the big O section. I definitely recommend you watch it if you're not sure about logarithms, if you were taught them a long time ago and you forgot them, or if you were never taught them. It's a quick video. So suppose we're searching for the number 13 in this array. How many steps does it take? Well, we actually can see 13 is not in here as a human. It should be right here if it were to be in this array. But the first step is to pick a midpoint. And I know this looks like it's not the middle, but these are all double-digit numbers over here, so it's kind of skewed. But this is the midpoint. So we pick 19 and we check, is 13 less than or greater than 19? It's less than, so we know it's somewhere over here if it's going to be in here. So then that's what this array is representing. We're not actually shrinking the array down, we're just looking at this portion of the larger array. So then we pick a midpoint again, which is 9. Well, 13, is that less than or greater than? It's greater than 9. So we're now looking at this subarray, 11, 14, 15. So we pick the midpoint 14. Is 13 less than or greater than? It is less than. So we're looking at this subarray now, 11. So we check, is 13 equal to 11? The answer is no, of course. And so we know that 13 is not in this array, unless it's somehow an unsorted array, in which case we shouldn't be using binary search. But given the conditions of binary search, we can say without a doubt 13 is not in this array. Nope, not here. So if we look at the number of steps here, we had 16 elements. It took 4 steps to say with certainty that an element is not in there. So we could have found it earlier if it actually was in this array. If we were looking for 9, for example, it takes 2 steps. If we're looking for 14, it would take 3 steps. But if we're looking for something that's not in there, or the very worst case, it took 4 steps. Now, 16 elements, 4 steps. Let's grow our array. Let's double it in size. So instead of 16, I'm adding 16 more elements. So we have 32 elements in our array. It looks like this. And let's say I'm looking for the number 32. How many steps will it take? Well, in the first step, we pick a midpoint. This is not counting as a step. This is just our starting array. I pick the midpoint, which is 16. And we test, is 32 greater than or less than 16? It's greater than. So we can ignore all of this. There we go. This slide took a long time to make. So now we're looking at this part of the array. And we pick a midpoint, which is 24. And we compare 32. Well, 32 is greater, so we can ignore all of this. Next, we're looking at this portion, and we pick a midpoint again. 32 is greater than 28, so we ignore all of this. Skip. Now we're looking at 30. Well, we're looking at this portion, and we pick a midpoint, which is 30, and 32 is greater than 30, so we ignore this portion. Finally, we pick our midpoint again, and we find 32. We're good to go. And that took 5 steps. 1 step, 2, 3, it's highlighting the wrong thing. 1, 2, 3, 4, 5 until we found it. So we doubled the number of elements from the previous slide. We had 16 elements, which was 4 steps to find, or actually we didn't find the element, but it took maximum 4 steps. Here, we doubled it to 32 elements, and it took a maximum of 5 steps to find our element. So that relationship is log base 2 of n. So log base 2, which we simplified to log n, basically means 2 to what power gives us n. So if we go all the way back here, 16 elements, what is log base 2 of 16? It is 4, because 2 to the 4th power gives us 16. 2 times 2 times 2 times 2. Or here, it was log base 2 of 32 elements. If n is 32, that means 5. 2 times 2 times 2 times 2 times 2. So every time we double the size of n, every time we double it, we are simply adding one extra step. So log n is really good. If we look at the big O complexity cheat sheet little graph here, you can see log n is all the way down here. It's really good. It's so good, in fact, they don't even put a separate line in here. So there's the O of n line, our linear big O. And then down here, they put constant and log n together, because in the grand scheme of things, when you zoom out far enough so that you're looking at something that also includes factorial, O of log n is so much better that it just looks like O of 1. Anyway, so log n is really good. Binary search is very fast. Of course, the caveat is that it only works on a sorted array, and if you don't have sorted data, then you're out of luck, and you've got to use linear search, which is not anywhere near as good. Going forward, we actually will see a couple other algorithms when we talk about things like binary trees and graphs, where the big O notation for time complexity includes log n again, or also n log n. So if you're not comfortable with logs yet, I really recommend you watch that video, but also give it some time. I think we have a couple sections before we encounter log n again, but soon we will.